When you have more complicated systems, such as this cart that's pushing back a spring at point A, and then it's going to fly, move with some velocity up and around the loop. When you have a more complicated system like this, you need to start thinking about exactly what is the system, and is energy being put into the system? Is energy coming out of the system, or is energy being conserved? And so, again, think about these definitions of open system versus closed system. In an open system, energy can flow in and out of the system. In a closed system, energy is conserved. So defining the system is really important. So if we define the system as the cart, the spring, the earth, and the track. So basically everything. If we define the system as basically everything, well, energy will be conserved. So if we say that there's no friction, then we might start out with all elastic potential energy. And then at point B, we're going to be looking at some kinetic energy and some gravitational energy. And the ratio of these would depend on how tall the loop is. We can now write our conservation of energy equation, knowing that we have elastic potential energy at the beginning. I'm going to use PES to denote elastic potential energy. The total elastic potential energy at the beginning will be equal to the kinetic energy at position B plus the gravitational potential energy at point B as well. So this would be 1/2 kx squared equals 1/2 mv squared, the velocity at point B, plus mgh, and this would be the height of the loop at point B. If we added friction, well, our gravitational potential energy wouldn't change because that just has to do with the height. So we would probably be going slower at the top of this loop, have a little bit of kinetic energy, and then a little bit of thermal energy. When you have friction, then the equation changes just a little bit in that you'll have to add this thermal energy here. Oftentimes, this thermal energy gets treated in a different way, and we'll talk about that later. If we were to take the spring out of the system, well, then the cart at the beginning has no energy. So the energy at position A, there will be none because the spring isn't part of what we're considering the system. And so we're going to have energy flow into the system due to the cart. So energy is going to have to go in. And if we're talking about conservation of energy, if we have 5 blocks of energy here, we would need 5 units of energy to be put into the system. Now, if we didn't have the track as part of our system, and there was friction, well, then we wouldn't have any thermal energy. That idea of thermal energy being lost is oftentimes lost due to friction. And so we would have a little bit of energy come out due to heat. This idea of energy flowing into and out of the system, this is what physicists define as work. Work being done on the system or work being done by the system. If we go back to the idea of the system includes the cart, the spring, and the earth, and then that means that energy is lost due to friction or work is done by friction, then when we write our energy equation saying that the potential energy of the spring equals the kinetic energy at point B plus the potential energy at point B, we also need to include the work done by friction. we will figure out, or there will be another video talking about equations for work and how you actually calculate that. For now, we can just say that if we knew everything else, we knew the spring constant, we knew the distance that the spring was pushed back, we knew the mass of the cart, the velocity, and the height of the loop, we could calculate the energy lost due to friction or the work done by friction.